Thanks for the introduction. I'll just get right to it. So I decided to give a talk today about some of our platform planning activities since we finally have made progress on something we've been working on for 5 or 6 years. It's time to get out there and talk about the thing you're going to do next. There we go. So we have lots of machines at Los Alamos. We've always had lots of machines, and we've had lots of machines almost forever. That's in the 40s. You see the progression of machines that we've had, and I think we've had about 130 machines in the last 50 years. And lots of varieties of sizes and things, capacity machines, lots of Broadwells. We bought a lot of those at the time. Trinity is still up and running. It's a 20,000 node system with 2 petabytes of DRAM and 4 petabytes of flash. And it's a workhorse. It's been a great machine. And we got a lot of stuff done on it. There was a reason it was purchased. It was purchased for a particular problem. That problem ran. It took 18 months to run on half of the machine. So 10,000 nodes, a petabyte of DRAM for 18 months to solve a problem. And then some other things. We keep an old system around, usually for scale test beds and things like that. So that's a really old system. And a lot of other systems too. Test bed for app architectures and all kinds of things. I'm just going to talk a little bit more about these recent machines we're installing or about to install. Tacoma is a sort of a general purpose machine with a lot of CPUs and a few GPUs. Crossroads is being installed pretty soon. Tycho is installed now. This is an open test bed, and I'll talk a little bit about our HPE NVIDIA effort that's going on, which is kind of exciting. So let's talk a little bit about the different kinds of machines and the different missions we have. So each lab in the lab complex has a different mission. And it's really quite a broad spectrum of missions. You talk about NERSC. They have thousands of users, hundreds of codes, and lots of variety. Los Alamos lives at the absolute other end of that spectrum. We have roughly 4 codes that eat all the time. And they're very big, complex codes, and they're produced by hundreds of people over 20 years, and there's 10 million lines and 40 physics packages, really big, monstrous things, right? And the Office of Science typically on the other end of the spectrum, lots of science codes written by graduate student program and things like that. I stole this from Giri Chickapalli from NVIDIA. He's probably going to be mad at me, but I've been using it ever since he was at Sun, so that's a long time ago. So along this axis, you've got control flow complexity, so think branching, if statements, and that sort of thing. Along this axis, you've got data flow complexity, so think sparsity, irregularness out here, and dense back there. And this is the way he classifies systems, and systems that are sort of in this low, very dense, and not very branchy. That's where things like AI and ML mostly live. This is where GPUs and things are for the most part. This is sort of where the cloud is. A lot of commodity-oriented technologies, just basically processors for the most part. And up here, we've got very, very complex data flow, so very sparse, irregular problems, high branching and things like that. And then down here, this is where IoT and things like that live. We buy 3 kinds of systems at LANL. We buy these things called advanced technology systems to run these really icky problems that are very complex and irregular and sparse and branch a lot. We buy systems that are sort of just commodity technology systems for running the mass workloads that we have. And then we buy some institutional systems. And this is to support just the general science at the laboratory, because we have mission science kind of stuff, and then we've got open science where it's much broader. And so these machines are typically 100 terabyte size working sets, a quarter of a machine. This is where simulation, AI, ML, all kinds of things run here. This is really warm-up kind of activities for running here. And these machines, there's a series of these machines that started with Trinity. Trinity was ATS1. And Livermore Sierra was ATS2, and then Crossroads is ATS3, and El Cap is ATS4. So Livermore and Los Alamos toggle back and forth. putting big machines in this ATS class.
Gary, what is
Yeah.
UQ on this slide?
Uncertainty quantification, so lots of statistical kinds of jobs are run in that space. Next slide. This is a schedule for just recent installs. This machine is now in and running in the secure. It's a SPR DDR system. This machine, Crossroads, is scheduled to be installed pretty soon. This is a pure SPR HBM all system. There's no DDR in it. And then this machine, Venato, is an institutional machine. And it's Grace and H100. And it's a little further out in time. So I'll tell you a little bit about those machines. Tacoma is a machine that's mostly CPUs. It's like, 1,800 dual socket nodes, so quite a few, 3,200, 3,400 sockets of AMD, and it's got some small amount of A100s in it. And this is, again, an open science machine. It's used for all kinds of problems. It's been a pretty good workhorse for us. We've upgraded it once, added more nodes to it. It was actually begun during COVID. It was part of the CARES Act. The CARES Act was produce computing for COVID research, and it's morphed into this. Next slide is, back on that slide, we also provide quantum services. So we had one of the first D-Waves at the lab a long time ago, had it there for I think about 7 years. It was upgraded twice. And we've just recently uninstalled it, and we've just gone to using quantum via the cloud. And so we actually have contracts with a bunch of different providers to provide quantum for our scientists to use too. Venato. So this is kind of interesting. This will be the largest U.S. instance of Grace H100 solution for quite a while, we think, in the U.S., and there'll be a bigger one in Europe. And it's this Grace, which is the U.S.'s first real HPC ARM class processor, really. It's going to be about 80% CPU and GPU and about 20% CPU only. So it's kind of the complement to Tacoma. Tacoma was mostly, CPUs. This is going to be mostly GPUs. But this is kind of interesting architecture, right? It's got full reticle CPU connected to a full reticle GPU with incredibly high bandwidth between them, and it's coherent. And that's kind of nice. And there's also some pretty interesting stuff about the CPU. The CPU is it's two full reticle sockets that are connected together by very high bandwidth. And the interesting thing about it for me is, besides it being ARM and the first US ARM chip, and it's got SVE and all that kind of stuff, is that it's kind of the first time in a really, really long time that there was a SMP where the memory connected to each processor and the speed between the processors are basically the same. So you can access memory at roughly the same speed from the other guy's memory as you can from your memory, which is not typical at all. Usually there's a huge NUMA effect, factor of 5, factor of 8. So this is pretty different. Why were we interested in this? We're interested in this because we do an awful lot of strong scaling. Those icky problems that are irregular and sparse and branch a lot, they also have horrible scaling because of all that. And so we need something that will scale, strong scale. And what is strong scale? It's using fewer processors, to get the job done, so that you can, because you can't scale very well. And the hope here is that you have a lot more bandwidth per core. That's the hope. I was hoping to be able to give you numbers because we've actually done some tests on it, but NVIDIA won't let me. Not yet, anyway. Our other systems we put in this system called Tycho, which is an SPR DDR system. It's a capacity system, CTS, and it's like 5,200 sockets or something. And this is in our secure environment. And then there's a small little test bed here, with some, 100,000 sockets or so total, some HBM and some DDR. This is in the open. These are kind of warm-up systems for running on Crossroads. Crossroads is here. Crossroads is 12,000 HBM SPR sockets almost a terabyte, almost a petabyte of memory. You might ask, my goodness, that's less memory than you had with Trinity. Why do you do that? And the answer is it's pretty expensive. The other answer is we think we're going to get more throughput through a smaller memory machine with way more capability than a bigger machine that you just have to run multiple jobs on. So we think we'll win. We'll see. And remember, it's all HBM. There's no DDR. And also, this is kind of weird too. Normally, when we would buy a file system for one of these large systems, it would be all flash. That's what this is. It's going to be about 10 petabytes of flash. But isn't that weird that you have only, you've got almost a petabyte of DRAM, and you've got only 10 petabytes of scratch file system? That's actually pretty low. Normally, that's a 30 times. Sometimes it's a 50 times for people. This is, again, a question of cost. And it's also a question of success. We actually have a storage system that sits underneath this called a campaign store that's half an exabyte or something. It's pretty big. And it's all disk. And it's all cheap disk. And it uses erasure and encoding and the like. And it really runs quite fast. We can write data to it in half a terabyte a second or something. So it's pretty fast. And so people can move data between these two things very rapidly. And in fact, that's even been integrated into the job scheduling management system of the Cray, the Cray orchestration layer, so that when you submit a job, it knows it needs to go get the data from the tier below, move it up, and all that kind of stuff. So we've had that capability for quite a while, and it's become so successful, we feel like we can get by with a whole lot less scratch file systems than we've used in the past. We'll see if that works too. I can give you some numbers about SPR. We actually got the okay from Intel to release these. This was in a paper at Supercomputing. You can download it. You don't need to memorize it or anything, but what you'll notice here is that this is compared to Broadwell, and these are speed up ratios, like speed up numbers, right? So it's 5 times or something of a Broadwell chip. This is the DDR, and this is the HBM version is more like 7 or 8 times. And you'll notice that this is kind of a factor of 1.5 to 2 DDR SPR versus HBM. And it's better on the bigger problem, and that's because the bigger problem is more complex and uses more memory bandwidth. And so really, it's probably closer, but it's over a factor of 2 typically. And you see the same thing down here. This is a real code. It's an asteroid hydrodynamics code that's heavy AMR Eulerian, pretty complex code. And then these are just benchmarks. You can see some ALE, some hydro, and the like. And those things are. Anyway, we're pretty happy about this. Factors of 8. From the last machine you bought hasn't happened to us in a long time. It's been a long time since we've been able to get that. And actually that rivals taking some parts of the codes and putting them on GPUs. You get about the same speed up. And the reason is mainly memory bandwidth. That's what we're starving for. So let's skip gears a little bit and let me talk about these really complex, icky, ugly codes that we have and what they do to our machines, and why I ended up buying, a great big CPU-only machine, and why there's not a whole crap load of GPUs at our site. And this is why. Back to Giddy's, nomenclature again, use it over and over again. We feel like we need to spend our time on things that other people aren't spending their time on. There's kind of no reason for us to go work with industry on making dense calculations go faster. People are going to do that anyway. We don't need to pay for it. And we actually don't have that much of that. We have a lot of sparse and irregular. So we live in, multi-scale, multi-physics problems kind of live up in this space. And so we've really tried to concentrate on that space. And that, on our ATS saga, from ATS 1 to ATS 7 or beyond, it's basically trying to solve problems in this space. GPUs, TPUs typically live down here. Again, just commodity systems live up there. So let's look at these problems. Let's tear them apart and look at them and see what's wrong with them. So the way they work is they move a lot of data around. They're memory hungry, memory bandwidth hungry. But what data are they moving around? So let's look and see. What am I spending my time on? Loads, branching, integer adds, array indexing, conditionals, stores, and that down here is floating point. And you'd think, well, shoot, you know, I'm an HPC sci, I ought to just love flops. I hate flops. Flops are a miserable excuse for trying to buy memory bandwidth, okay? So we spend 60% of our time talking to memory. And what are all these integer things? Why are we doing that? Well, that's index lookups to try to figure out where the data is for us to go work on. And control flow. What about all this branching and stuff? Boy, is that ugly or what? That's neutron transport. It's like ray tracing. You got neutrons, and they're going this way. And then when they get there, you got to go through 19 if statements to figure out where they go next. And when they get there, you got to go through 19 if statements to figure out where they go next. And you can't imagine what that does to a computer. You know what kind of computer runs that kind of workload well? A 10 gigahertz computer that doesn't exist. That's the only thing you can throw at that problem. And so this problem is really hard. And this problem is really hard because it's not just memory bandwidth, it's also memory latency. So this is a heat graph of where we're having problems. And you can see that we're not having problems in floating point and vector. In fact, we only have one code, the neutron transport code, that uses any floating point at all, any kind of vectorization at all. It's all here. It's all in memory bandwidth, memory latency, and branching activity. That's where all our problems are. And so it's not all about flops. And in fact, that's why in our bids that our RFPs get answered by, and we go through our analysis, and why the CPUs always win. Because of this. It's not that we love them, it's they win.
And it's all mostly all cache, too.
Let's talk about cache. Good, cache. Let's talk about cache. So cache is cool. Cache is wonderful. This is a breakdown of cache line use. Purple is 75% of the cache line used. That one's 50%. Blue is 25%, and these are down in the dust. And you can see sometimes we get to use cache, and cache is wonderful when it works. But look at this. We pulled those four things apart, and we put them here. The blue is integers in the cache. The orange is floating points in the cache. Do you think I care about integers? I could care less about integers. Integers are just a nuisance. But that's how I address to figure out where my floating point numbers are. So guess what happens? The cache just gets full of indices on how do I access my sparse data. And it's full of it, and that's all I'm moving. And this is why I get so little flops. Let's dig a little bit further. First, let's back up a little bit and admire Karen Bergman's work, because we always like to talk good about Karen Bergman. And she talks about this imbalance and how flops are up here and memory bandwidth is down here and so forth. And this is a log scale, folks. This is a log scale, okay? That's how bad it is. And let's talk a little bit about benchmark. So HPCG lives there. That's supposed to be a sparse benchmark. Where's floating point? It's over there. Or where's LINPACK? It's over there, right? That's LINPACK. This is This is HPCG, and it's supposed to be the winner on being sparse and irregular. Well, guess what? Not really. There's a lot of apps that live here, and most of my apps live here. Those are roof lines. That's for DRAM, L2, L3, L2, L1. This was on a Broadwell, I think. Doesn't really matter. They all look the same. This is where a lot of applications live, and this is where LINPACK is. Okay? So we're inciting people to build the wrong stuff for us, which is not so good. Why is this so horrible? Why are workloads like this so horrible? And it turns out that it's the data structures used. So if you think about an AMR problem, it's a 3D problem, and let's just take something simple like cubes. So it's got a bunch of cubes, 3D cubes, 1 trillion of them spread out across 1 million memories. And every time step, something fun happens in the physics, There's some high entropy thing that's going on, and the AMR goes, I'm going to drill in on that, and I'm going to make more cubes there. And to make space for that, I'm going to take some of the cubes away over here and some of the cubes away over here. And then the next time step, that high entropy thing is moved because it's moving at some ungodly velocity in our world or something, right? And so it has to redo it all. And so it redoes this whole mesh and figures out I got to drill in here and I got to drill out there. And so what's happening to the underlying floating point values going on? Your neighbors are changing. You get bigger neighbors and smaller neighbors. So the only way to deal with, there's two ways to deal with this. One, every time you just write the data out, flatten it out, and read it back in again. Remember, this is a petabyte. So that ain't, I'd get a time step per 10 minutes. That wouldn't work. The other way is to use indirect, use pointers, use indirection. Well, guess what? That's what we do. Why do we even do this? Why do we do this silly AMR crap? Anybody know? It's because we're trying to run a problem that's 100 times bigger than the machine that we bought. Crazy, but yeah, that's what we do. And so you're trying to run this huge problem that won't fit, and you're using these sparse, irregular representations that are changing all the time to do it, and it's causing you to have to go through indirection to get to your memory, and this is what that looks like. Right there. That's an indirection array. That's an indirection array, and this is where the floating point values live. And so I go into a loop, because everything we do is a loop, right? I go into a loop, and I go through this monotonically increasing, and I say, look up that floating point value, and it's got to go to that one and to that one to get that. And so what happens is I start in this loop, and what happens is the cache goes, damn, he's reading that serially. I'm going to put all of that in cache. Bring it on in. So I get a whole crap load of integers in cache. It's great. It's wonderful. And then I even get some of this layer. But by the time I get here, every op is a cache miss. Poof, I'm at 1%. Done. Can't go any better than that. Just gets worse from there. So that's what's wrong. How do you fix that? One way to fix it is to get more memory bandwidth. Because if you can just speed all of that crap up, it'll go faster. Why do you think I was so interested in paying, 8 figures to try to get ThunderX4 out of Marvell to get me 2 terabytes a second of memory bandwidth on a CPU? That's why. That right there. I just wanted to take a hammer and beat the crap out of memory bandwidth so that I could just win by using a massive hammer. In fact, we're one of the main reasons there's an HBM part from Intel. Had we not gone through that effort, it's not clear they would have done that. And so, anyway, I get out my big old hammer and I get a 4X, but that isn't really what we're after. It's really inefficient. It's still horribly inefficient. It's just faster inefficient. So can we try to go fix it in some more elegant way than just throwing the hammer at it? Because I already blew the hammer. I bought it. I'm using it. We're on this new path with HBM. That's it. That hammer's gone. I got to go do something else. So what do we do? What do we look for? How would we go fix this? There's been some interesting work at Berkeley to look at this, and I'll explain it in a minute. But anyway, that's my hammer story. And there's a lot of problems, not just ours, not just weirdo nuclear people, that have these problems. And this is not my work. This is just stolen. But there's a lot of problems that are very, very sparse and irregular. One of them that's not up here that I think is super interesting is recommender systems. So a recommender system is like all the products that Amazon has on one axis and all the products that I've bought from Amazon on another axis. You know how sparse that is? That's incredibly sparse. It's incredibly irregular. And if you want to go do math on that, guess what? You build an indirection array and you start looking stuff up indirectly because that's the only way to do it. But there's a lot of other genres out here that suffer from these same problems. They don't happen to be super popular, but they're still there. And it's not that I hate GPUs, it's just that somebody says, including me, that GPUs aren't good at this particular thing. If I could turn my workload into something that was prettier for a GPU, I'd do that in a heartbeat. It'd be great. In fact, I hope I get to do that. what was the effect of that on, say, buying Crossroads? So we went and bought Crossroads 2 or 3 times trying to convince somebody to put an HBM part on a CPU, and we've been at that for the last 6 years, but how did it actually turn out? So this is a machine back in 2011, an AMD system, and this is Trinity. Buying Crossroads, this is bid 1 and bid 2, and this is a GPU system. The peak flops has got awfully big. And over here you see that SSI apps, these are applications that mimic what we do. They're not our full applications because they're classified and you can have them, but they mimic what we do. The applications can be modified by the vendor to their heart's content as long as they're solving the same problem. And we basically measure, before and after they optimized, how much did they optimize, what did they do to it, and all that kind of stuff to try to figure out what to buy. And so this is a massive app optimized CPU, GPU bid. That is, blue is no app change. This is with app change, and that's peak flops. And then we got another bid that was CPU plus another accelerator, CPU HBM plus another accelerator. Again, very, very large numbers of peaks. Not as much difference here, but the whole thing is higher. And then we get into 3 CPU bids with HBM. And guess what? Without changing the code, they're better than after spending, changing most of the code to try to work, because it's just not amenable to this. So these are the 3 bids that really got looked at. And this is the effect of all this, which is why we worked so hard to try to get solutions in this space, because people that have these problems need help. What kind of what are we trying to accomplish here? Well, we're trying to run a problem that's, like I said, a petabyte in working set size. And today on Trinity, they run 6 to 18 months, 12 months, a long time. How do people learn if they get a result every year? They don't get to talk to their neighbor about it like the person that was before me. It's not very collaborative in nature. It's really hard. It takes a real hero to go do this and to try to learn from it. It's not very practical. What do we need to do? We need to get need to get this down to days, so that you get a result a week, or you get a result every few days, so you can talk to your collaborators and you can learn from it from a science point of view, and you can write papers and you can do all the things scientists do. We got to move from the 1% efficiencies up to something like 30% efficiencies, and we kind of need to do that soon, because these are really important problems that we're trying to run, and we've just got to change the way this works to make it self-amenable to human learning. That's essentially what we're trying to do. And so how are we doing that? We're leaning on tailoring of architectures, getting HBM on package, other kinds of tailoring to try to make this better. And so there's been a saga here, and I'll take you through that saga in a minute, but it involves these ATS systems we buy. And here we go. So I'm a fan of caveat diagrams. In the ASCII program, we used to use caveat diagrams all the time. And you can see that I picked some interesting axes here. Reconfigurable, branchy, assist kinds of things, memory bandwidth, computation near storage and in memory, or in network and storage, irregular memory access, AI and ML assist, memory capacity. And you can see Trinity. Trinity is this red thing. A lot of capacity and nothing else, right? But the question was, can I run the problem at all? And it wasn't easy. Why? Because I had a petabyte of working set that I had to dump off every 30 minutes. So I had to invent burst buffers, which is kind of a weird term, just a bunch of flash. But I had to invent that so that I could dump the stuff off to keep the thing going long enough to get the job done. So there was a lot of work done here trying to figure out how to use flash inside of systems to be able to do very, very fast multi-terabyte per second dumps so that you can keep these things moving forward. All that work, that's what that was for. It answered the question, can you run it? It's just damn slow. The question we're asking with Crossroads is, could we speed that up significantly, like the answer, 4 to 6 times? And we think the answer is yes. Why? Because we got 5 times the memory bandwidth. Why? Because we paid somebody over and over again for 5 years to convince them to build a damn processor and put HBM on it. But we got there. What are we going to do in ATS-5? How would you go fix this problem? The problem really, to get it from weeks to days, you're going to have to get another factor of 3 or 4. How are you going to fix it? Well, that's this blue line, which is going to have almost as much capacity. Way more memory bandwidth, that's Crossroads, right? The next one after that is this green thing, which is going to have capacity and bandwidth, but it's going to take care of irregular memory access. So how in the hell are we going to take care of memory access? How are we going to address this icky problem? That thing. How are we going to do that? Well, the beauty of that thing is we're in a loop, because we're always in a loop. And we can unroll loops. We've been unrolling loops for as long as I've been around and longer. And we know that we're going to access that thing in that order. So we know at the top of the loop that we need to go look up a few hundred, maybe a few thousand, maybe a few million lookups. So we could maybe build some hardware and give it a whole vector of things and say, hey, go do all these lookups. And it's very parallelizable because we're going to give it a lot. And so it's possible to maybe build some kind of a piece of hardware that has way more memory controllers than has anything else on it. So a crap load of memory banks and a crap load of memory controllers to work in parallel to build me a dense data structure so that I can finally use a vector or a SIMD unit or something to go do this math, right? And so that's what we're going to go try to do. We're working with some memory companies, we're working with some processor companies, and this is going to be another one of those sagas, right? Just like trying to get HBM on a processor, we're going to go try to get this done somehow, and we hope we'll get there. We think we will. So that's how we're going to go try to address that icky stuff and and drive that number down, right? Way more irregular memory access capability. And the other thing, of course, we can do is we can use AI and ML assists where we can, and everything else we can think of to try to help us, including computation in the net and storage. And we have some interesting work going on in both of those places. But the bulk of what we're trying to do right now is go try to figure out what it would take, how many tens of millions of dollars do I have to spend in industry to get a demonstration of that to work by 2026, 2027, which was the time frame. And then this last machine, of course, I'll be gone, won't matter, but hopefully it's even better in all these cases. But the one thing we're going to try to really address then is the branchiness. And we have some pretty good experiments going on in that space. We think coarse grain reconfigurability may be part of the answer there. You all probably know that there's some coarse grain reconfigurable technologies out there. So we have some of those we're playing with and funding and some big companies and some small companies. And so anyway, we think we can attack. We think we can win that war at least as good as it can be won through parallelism. And we think we can address this through reconfigurability. And then the last, since I ranted about memory bandwidth, I thought I would give Jack a plug. Shortly after his Turing Award, people started listening to him again. It's because it wasn't all about flops anymore. He had a new story, right? And the new story is we need memory bandwidth. I won't read that whole thing to you. I'll just point this out, that a divergence of 100 or 200x is in fact a performance in economic crime. He's basically saying if you buy so many flops and you don't have any memory bandwidth to feed it, all you're doing is heating the earth. So anyway, that's, I think, what I had to say. I was actually at the lab at this time, so I'm quite old. That wasn't me because I didn't ever have that much hair, but that's a CDC 7600, and that's a Cray 1. Interesting story. So we were at supercomputing last year, and HPE, of course, they bought Cray, and they had the Cray 1 serial number 1 in their booth. And it was from Los Alamos, because we got the first one in 1976. It didn't work. It worked in Minnesota and it didn't work in Los Alamos. Why? Because we're at 7,600 feet and Minneapolis isn't. Well, guess what? They had put any sec dead, any protection, any erasure, anything on the memory. So the people that know Craze well, at least a lot of people at the lab, walked by that and they said, Gary, why is that machine so short? It's just about that tall. And every other Cray one was bigger, was taller than me. And they said, why is this one short? And I said, because they had to send it back and they built us one with another row, which every row of the memory bank was about a foot. Because remember, these were transistors. They were ICs. And so from Cray serial number 2 to whatever, they were taller because they had an extra row of parity bits at the top. Interesting story. So I don't know what else to tell you. I'll take questions, I guess. Shoot.
No, you go first, and I'll take him next. You guys with a tie.
Hi. So the question I had was, has anyone looked at the characteristics of your indirection arrays? Are they single valued or multi-valued, or do you have repeats in them? So like, for instance, C sub I, does it point to...
Are there patterns?
Yeah. And so has anybody tried sorting the data?
Yeah, we actually do that. In fact, I simplified it. So we actually have more than one type of indirection array because one of them walks around the neighbor pointers, the edges. One of them walks around the corners. One of them walks the Hilbert space. And so there's several of them, and each different loop will attack it a different way. And so there's several. There are patterns in some of them. There aren't patterns in others. We do sort them where it's beneficial, and we don't sort them in other times. The other thing that I'll mention that's probably related to this, which I think is really cool work, is we use these SSI benchmarks. And the SSI benchmarks are pretty cool because they sort of mimic what we do, but they're really codes and they really do computation. And there's kind of no reason for it. I think I proved that there's no reason for us to provide an SSI with any flops in it at all. It's all about how you access memory. So we wrote some tools to capture memory location references. And then we've been funding Georgia Tech to build this really cool tool called Spatter, which is a memory location replayer that makes up things and does it for you. Really cool. And so our next buy will actually have probably more benchmarks that are Spatter pattern benchmarks than actual codes. And it's free. You can have it. All those tools are free. It's pretty cool stuff. And yes, that we've looked for, and we also have machine learning people looking at, can I find patterns? Yeah, we've done a bunch. A lot of universities are getting paid to dig on this. And there's some good stuff happening. It's not all bad.
Hi, Gary, thanks for the talk. Addison Snell, Intersect 360 Research. I'm going to ask, I'm curious about the story behind your Kvyat diagram. If you want to pull it back up, I'll start asking the question. Just a curiosity in it I wanted to ask about. I get that it says that it's notional. There's no units on it, so 1 at the outside could be absolutely anything.
Yeah.
And so ATS7 is on the outside on every axis of it except branchy assist, which it might as well be. What would have gone all the way? Was there some other technology either that exists or that doesn't exist that you were hoping for that is on the outside of that axis? Because you could have drawn it that way where
Yes,
it's on the outside everywhere. So what's the imaginary thing that's out there that you're not getting?
It's reconfigurability, but done a whole different way. Sorry, I can't say much.
There's something you had in
That's
mind
right.
out there that's not on the chart.
There is absolutely something we have in mind there. You're right. No question about it.
Okay.
He's not going to tell you.
I've got to justify ATS 9, right? I won't be here. It didn't matter.
You don't want that question. You got to fix that chart.
I just had a quick observation. I'm no quantum expert, but I've been listening to a lot of quantum stuff, and the biggest thing I've been hearing for the best apps that are, suitable or candidates for quantum are apps that are modeling quantum effects, which just seems like what you're doing. So I mean, the quantum thing seems to be some
Yeah,
of this
that's somewhat true.
dealing with
certainly.
orders of magnitude more per cycle, if you will. Yeah.
We've had some pretty cool work with quantum. I think the coolest stuff is really not the. I mean, the quantum key distribution work has been around for a while, and that's pretty cool and is used a lot. But quantum measurement, this using quantum effects to measure, you can finally measure, sub-angstrom things, which for some industries is pretty cool. And so I think that's one of the biggest, coolest things about quantum right now. I'm not sure it's quantum computing. We actually had good success with our D-Wave for local minima optimization problems. Those are hard, take a long time to do if they're doable at all. And so we used that for working on these problems, help us, to figure out where to go. And of course combinatorials, but of course you can't buy enough qubits to do that for real yet. But we're looking forward to that because there are aspects that we could potentially use. So we're bullish on it from a long-term point of view. I am a little worried, right? There was a couple of the VCs are starting to pull back. I don't know if you saw that. It was in the news from some of the quantum startups. And I kind of thought this might happen, A, because the economy is tanking, but B, we tend to do this, right, in the U.S. We overinvest in something that's hot and neat and then gets a bunch of spun up, and then we leave a bunch of people high and dry. It just seems to be the way it is. I don't like it, but
the hype cycle and the fact that many of these are going public way early too is not healthy
but
either.
we found uses for the D-Wave. People, just like every machine, everybody hated it when you put it in, and then you couldn't pry it out of their cold dead hands to get it out. It's always true. It was true even with that machine. But I got a nice deal fridge out of it, so I can use it for something else.
Hey Gary, just curious about your AMR problem. Is it like completely unstructured measures, or is it more like octree based or structured AMR? And does that help with your irregular memory access?
Completely unstructured, and it's largely cell-based, although there's some variants of it that will use block-based for a while until the entropy gets really high. And then they've had trouble with it converging if they don't go fine-grained, so they turn on, which unfortunately for us, the entropy is high a lot, at least for the interesting part of the problem. But yeah, we've played with mostly just block-based AMR kind of approaches to try to speed up parts of the problem, and that helps some.
Let's thank our speaker.
We'll go fix it.